Thank you for making the time to attend this event. We have a very special panel today that has joined us. But beforehand, I just would like to introduce myself. I'm Isabelle Boscaro-Clarke. I'm here actually instead of Sandra Ribeiro, who is the chair of lightsources.org. I'm standing in as vice chair, really, to give you a little bit of a welcome and an introduction to this session. I'll be joined by Ashley White, Director of Communications and Interim Director for Strategy at the Advanced Light Source in Berkeley, who will be moderating the session with the speakers. So I wanted to give you a little bit of background about lightsources.org. Everything started back in 2004 when there were just a handful of light sources interested in gathering up to create a little bit of a one voice for the science that we represent. And just almost 2 decades later, we are standing in at about 25 members strong, representing 30 facilities and with a mix of synchrotrons and free electron lasers. So it's a very big privilege to be here representing this collaboration that has grown over the years down to the commitment of all the key members that have joined along the way. I wanted to also thank all the scientists that are here today to come and broach the subject of 4th generation light source, because this is a field that has been really pioneered throughout with technology improvements, and it's been a fantastic it's been fantastic to be part of that history. And it's wonderful to have Max 4 and that is based in Sweden, and Sirius in Brazil, and ESRF in Grenoble in France, which is the European light source. So we're very fortunate to have these speakers to come and really showcase what the technology can now do and what it can do to the science that we deliver, most importantly. And without delay, I just wanted to lastly really dedicate this webinar to Professor Ian Munro, who sadly passed away last year, who was actually part of our 75th anniversary celebrating the discovery of synchrotron light in the laboratory about a year ago. So really Ian was a pioneer in the field, and he was working at the Daresbury laboratory for all of that in the early 70s. And he amongst many, shall we say, were visionary about what it could do for the scientific base. And we are very grateful because we are really in debt to that vision. We've got globally, I'm sure, close to 50,000 users that are benefiting from that light. And he was an enthusiast. He brought people together to collaborate, really somebody that just inspired collaboration for science and science diplomacy. So, and without delay, I just want to thank Ashley, who will take us into the part that will be moderated for our great speakers today. So thank you very much.
All right, thank you, Isabelle, for that introduction. We have an exciting program in store for you today, focused, of course, on 4th generation light sources. Here at the ALS in Berkeley, we are deep into an upgrade of our own facility to transform it into a 4th generation light source. So I'm excited to hear from these folks who are already working at these types of facilities. So let me just review how we are going to run things over the next hour. Each of our panelists is going to give a very brief intro, and then we have a set of questions that we'll go through that we put together in advance, but we also want things to be interactive. So as we go through, if a question comes up, go ahead and put it into the Q&A feature that you can find at the bottom of your screen. And we'll try to get to some of those questions kind of during the discussion, but also try to leave some time at the end for questions on topics that we might not have addressed already. So let me just quickly introduce our 4 panelists before we dive into their introductory talks. So first up, we have Monika Bielczyk, who is a PhD student at Max 4 in Sweden. Her work is focused on serial synchrotron crystallography and its implementation at the Biomax and Micromax beamlines. Georgi Dakovsky is a lead scientist at LCLS in California. His current focus is the NEH 2.2 beamline for LCLS2. This beamline will enable new ways to capture rare chemical events, characterize fluctuating heterogeneous complexes, and reveal quantum phenomena in matter using chemical, site, and orbital-specific resonant techniques that are possible only with X-ray lasers. Graciela Cedeno is a user at Sirius in Brazil and is researching biocatalysis and conducting experiments on the Carnaúba beamline. And Marta Mirolo is a postdoc working on ID31, the buried interface beamline at the ESRF EBS in France. She is working on batteries in the framework of different collaborations in battery research. This includes characterizing all sorts of different batteries, including those made of lithium ion, sodium, magnesium, or potassium with liquid or solid electrolytes. So I will now turn things over to Monica to kick things off by telling us about her facility and her current role.
Okay. Hello, everybody. Thank you, all of you for joining. So I will just quickly say something about myself and the facility that I work with. So the synchrotron that I work with is called Maxwell Laboratory. It's located in Lund in Sweden. I'm a PhD student and I started in 2019. So I'm a pre-corona baby on that. So just quickly about Max4. So it's a 4th-generation synchrotron. This is how the schematic looks like. Most importantly, we have 2 rings. So we have one small ring that gives 1.5 GeV and a big ring that gives 3. And of course, all that's instituted also with the LINAC that powers the whole beam. Currently, as you can see, the full lines represent the current beam lines that are in operation or in commissioning, and the dotted ones are the ones that are currently either in funding stage or they're being built. So as Ashley nicely introduced, I'm working on 2 beam lines. One is called Biomax, and this is the representation how the hatch looks like. So as I'm aware that there are some people that have never worked inside the hatch like this. So as you can see, we have a very complex thing, but the main important thing is, so where it's written RNX ND3, that's where you put your sample, and then that's where the whole magic happens of collecting protein crystals. The next big one is Micromax. That one is currently in the commissioning stage, so we are still not in full operation, but we will be by the end of this year. It has a similar way how Biomax works, but slightly different, which will be explained later during our questions. And then lastly, what my research revolves, as Ashley said, it's developing cellular crystallography for both Micromax and Biomax. And on the next slide, you can see some of the methods that I have been working on. Thank you.
All right, and next up, I believe we have Georgi.
Okay, thank you, Silvana. Maybe you can advance to my first slide. Okay, well, good morning to everyone. Thank you for attending this webinar. I work at the LINAC Coherent Source, which is actually one of the 2 light sources that we maintain at SLAC National Accelerator Laboratory. We also have a 3rd-generation synchrotron there, SSRL. But I fell in love with the LINAC. So what you can see on the left-hand side is an aerial picture of the LINAC, which is in Menlo Park, California, which is about 30 miles south of San Francisco. What you see is approximately a 3-kilometer long building, which houses actually at the moment not 1, but even 2 LINACs. We have the original linear accelerator, which is based out of copper structure, which is what we've been using for the past almost 15 years, ever since we came into operation in 2009. And that occupies the last third of the structure here. The first third was actually turned into a superconducting niobium-based accelerator that's actually currently under a very cold temperature, down to 2 Kelvin. And this will allow us to upgrade our facility to almost a megahertz repetition rate machine, which will be almost 4 orders of magnitude increased in average brightness, which makes us very excited. This will allow us to do actually a much broader portfolio of science experiments. What you see on the main part of the picture are the experimental holes. We have the near hole and the far hole. Most of the experiments in the near hole are based on soft X-ray infrastructure and instrumentation. We actually have a second floor, which houses the Chemrix and the Curix experiments, which are part of the monochromatic beamline, and that's where I work. The experiments in the far hole are mostly hard X-ray experiments, 0 femtosecond crystallography, matter in extreme condition, correlation spectroscopy. And these folks, they will get their upgrade to a superconducting operation about 3 or 4 years from now, where the second third of the LINAC will be actually populated with more cryomodules that will allow the electrons to be accelerated to even higher kinetic energy. So we can actually serve a very broad community. And most of the experiments that we do are in this pump probe configuration, where we have an optical pulse that triggers a reaction in the samples. And shortly after that, we arrive with an X-ray pulse that can interrogate the sample, and then we can use one of the very well-established techniques from our synchrotron colleagues, absorption, emission, resonance scattering, and so forth, to actually investigate the behavior on samples on a very, very short time scale. So we can produce pulses that are nominally on the order of 50 femtoseconds, but we actually have techniques to produce even out-of-second pulses, which are a billionth of a second, so very, very short phenomena. The soft X-ray monochromatic beamline, we have 2 instruments in series. One of them is dedicated for samples in solution phase, and that's called chemistry, where we literally flow liquids inside vacuum, and we measure their transmission or their X-ray emission spectroscopy, and we can deduce the chemical structure and the electronic structure and how quickly that evolves in time. And the other instrument is called Curix. That's where we study condensed materials, solid states, or very thin films as well. In those cases, there is the picture. We usually cool the samples down to very low temperatures, because that's where the interesting physics is. And the most interesting method of interrogating the sample there is based on this technique called resonant inelastic X-ray scattering, which in the middle of the picture, you see a very large scale 6-meter X-ray spectrometer, which allows us to deduce very low energy excitations in this material. So I think that's all from me, and I'll be happy to talk more later. Thank you.
All right, thanks, Georgi. Next up, we have Graciela.
Hi, can you hear me? Okay. Hi, everyone. Thank you for the opportunity to show a little bit of what our group from University of São Paulo has performed in the 4th generation series source at Brazilian Synchrotron Light Laboratory. In this work, we studied the bioelectrocatalytic mechanism for water splitting. For that, we used in situ X-ray absorption on spectroscopy at Carnaúba beamline. This is one of the 11 beamlines under operation in series. So we studied the bioelectrocatalytic mechanism of water oxidation by bilirubin oxidase, that is a multi-copper oxidase enzyme. This class of enzyme shows 4 copper ions in its active site, which can promote the reversible water oxidation reaction at specific conditions. So by using in situ X-ray absorption and spectroscopy, we monitor the oxidation state of these metal ions under electrocatalytic conditions. In this experiment, our sample holder was a miniaturized electrochemical cell, and the enzyme was immobilized on a carbon-based working electrode, as you can see in this figure. The bioelectrode was placed in front of the beam of the X-rays that hit the biocatalyst. With this cell, we were able to apply suitable electrochemical potential for the reaction and measure the water oxidation current while X-ray absorption spectra at the copper K age were collected. So the most interesting part of this study was to obtain high-intensity signals. For that, we acquired fluorescence maps on different regions of the electrode. Each pixel comprised 500 nanometers, assuring that higher intensity regions could be selected to finally adjust the incidence position to the sample. This extremely detailed observation of how the enzyme behaves during the bioelectrochemical reaction was only possible because of the 1st generation light source, which provides sufficient beam collimation, emittance, and brightness. So we could observe that the edge energy increases with the potential in region where the oxygen reduction is favored, indicate that enzyme copper sites are oxidized with increasing of the applied potential. Additionally, the edge energy decreases with the potential, when the potential is further increased to favor the water oxidation reaction, indicated that the copper ions do not remain oxidized under water oxidation conditions. So the X-ray absorption on the spectroscopy results suggest that the copper ions are reduced by the fast electron transfer from the water molecules. Our results corroborate the previous computational prediction from water oxidation mechanism, and we could calculate the driving force for water oxidation reaction, that is 1.8 electron volts, and the energy balance that for this process, that is 0.8 electron volt. So X-ray absorption on the spectroscopy demonstrated high sensitivity toward the in situ detection of copper catalytic sites during bioelectrocatalytic water oxidation reaction by this enzyme.
All right. Thank you very much, Graziella. And last up, we have Marta.
Yes, so hello everyone. Thank you for inviting me to this panel session. It has already been very interesting. I already learned something from other fourth generation synchrotrons. So I'm here from the European Synchrotron Radiation Facility, the ESRF, which is located in France. It's the European synchrotron. So we welcome visitors or users from all over the world, but mostly from Europe. The bit of history of ESRF. So we had the first electron beam in the storage ring in 1992, so 31 years ago. But the user operation started in 1994 with, let's say, only 15 beam lines. After 24 years or more than of operation, more than 20 years of operation, the ESRF went into shutdown for the upgrade to extremely brilliant source, the EBS. And we reopened to user operation in 2020, and the ESRF became the brightest synchrotron light source in the world with more than 40 beam lines. That's when I joined the ESRF. So I come from a background more on batteries and the use of spectroscopy. I wanted to enlarge a bit my knowledge about spectroscopy, about characterization, let's say, in general. So I decided to join ID31 to perform scattering measurements on electrochemical system in general. So just to give a bit of an idea of what do I do in my, let's say, daily life, just view a bit of what is my job like at ESRF. I have my own research on batteries, so that's what I mainly do, is my main topic. I also supervise students, so I study both batteries with solid electrolyte or liquid electrolyte with different setups, let's say. I also do a lot of user support, especially for users coming with experiments on batteries and electrolyzers, from the setup preparation to the experimental execution, and in some cases also the data analysis for some users, for some collaborations. I also do some student guidance, especially for students who come to our beamline for measuring some samples and they don't know how the beamline looks like, what kind of scattering, what kind of measurements we can do, how to analyze the data, and so on. And I also really like to advertise ESRF and ID31, not only at conferences, presenting a bit what we do, which kind of science we do, but also showing the beamline, showing the ESRF to different groups, coming, let's say, scientists or public coming to visit the beamline, but also I was very proud recently to show the beamline to a metal group, metal band from Italy who came to Grenoble for a concert, and they asked to visit the beamline. So it was a pretty cool visit that we had recently. So that's what I mainly work on: batteries, electrolyzers, and high energy scattering. And all of these thanks to the bright source of ESRF. That's a bit in short what I do.
All right, thanks very much, Marta. So now we are going to get into our panel discussion. And once again, as we go through these questions, if you yourself have some questions that you would like to ask the panelists, please do use the Q&A feature. We will, I'll try to keep an eye out for that, and we will work in as many questions from our audience as we can. So what I wanted to start with in this discussion, thank you. You have each told us a lot about what you do at your facility, but let's talk about actually how you got into working at Light Sources and a little bit about your career steps to get there. Now, Georgi, I think you've been working at Light Sources a little longer than some of our panelists, so maybe you can kick things off with how you got into it and kind of what your career steps were to get you to what you're doing today.
Thank you, Ashley. Well, I will start by saying that I will say something that I heard from somebody else, which is that career paths only make sense in hindsight. Yes, of course, if I look back, it seems like I was almost destined to work at this facility, but that's not actually how things happen in real life. So I first started by studying laser physics back in Bulgaria when I'm born, and that was in the mid to late 90s. I then moved onto the United States to pursue graduate studies, and I got more into spectroscopy and how we can do that with lasers, which initially was just tabletop spectroscopy, first in the terahertz range, then with high harmonic generation. And then it was kind of the middle to late 2010s where the LCLS was just about to come online, and just the breadth of science that you can do with X-rays, and the fact that I can actually continue to do ultrafast spectroscopy, but this time to extend to the X-ray regime was kind of a very, very appealing perspective to me. So that's how I kind of wanted to kind of extend my career and to venture in a realm of physics that I had actually no expertise before that. So I don't have synchrotron experience. I have experience with lasers in a small lab, but to kind of extend this to kind of a new horizons was very appealing to me, and that's how I ended up at LCLS, and I've been here for some years now.
Yeah. Thank you. Now, Monica, I know you mentioned that you as well, you did not kind of start things off at a synchrotron. You started as a synthetic chemist, I think. Could you tell us a little bit more about that career path and how you ended up working at a synchrotron?
Yeah, so I think even though like there's few years between Georgi and me, we kind of also had a similar thing that the path didn't directly follow to come to a light source, but life kind of happened and that led me here. So as you said, I started as a synthetic chemist. So my official current degree before I graduate is a master's in physical and inorganic chemistry. So nothing that I'm currently working, which is structural biology and developing of methods for them. So how I got into this isn't very a direct path, and it mostly life and experience led me to this. I went a bit around the world in different labs, from Singapore, from Germany, from Italy, and then I luckily stumbled upon an ad for this PhD position, which sounded very interesting. I had very little background in crystallography. I had small regarding the small molecules for inorganic chemistry, but nothing compared to what I'm currently doing. And then, that's how I stumbled upon coming to a light source. And in hindsight, similar how Georgi said, it's great. I would recommend that to everybody to come at a light source in any way they can. But it wasn't a straightforward path directly going to a light source.
Yeah. Let's go over to Marta now. Marta, I think you mentioned you had kind of gotten into synchrotrons first through a master's program, got an internship, and actually one thing that I wanted to pick up on, Monica was just mentioning how she kind of went all around the world working at different places. You were highlighting in your intro kind of the international community that you work with at ESRF. So could you tell us, a little bit about your career path, and maybe also throw in there what you think of this kind of international community that light sources tend to engender?
Yeah, so first of all, for me, that's the best thing, like to have these, like every week we have like people from different topics, from different countries, from different laboratories coming. So I don't have to go and visit different laboratories. They're coming to us, so it's actually pretty convenient. That's the best part. We always like get insights, let's say, or like we learn something new from users. That's fantastic. That's the best part of the job. I started, yes, at ESRF when I was a master's student. I had the opportunity to do an internship here, and I basically never left the synchrotron because I really enjoy this environment that is created inside the beamlines. I did my master thesis also here at ESRF, and then I took a break from ESRF. I went to the Swiss Light Source for doing my PhD, where I was like focusing on batteries and how to investigate the surface evolution with different spectroscopy techniques. And then I took the opportunity of the reopening of the ESRF to come back here. And I hope that they're not kicking me out, because I want to stay here forever. It's a beautiful place, and it's this, like last week we had experiments from the Netherlands, and the week before from France, and 2 weeks before, I don't even remember where they were coming from. They come here with their setup. The users, they teach you how to use their setup. You teach them how to use the beamline. There's this, community of like, we all want to learn something from the others. I think like large scale facilities, they have a bit this spatial environment. It's amazing to work here.
Yeah, it's certainly one of the aspects I have enjoyed most as well. Maybe we can go then to Graciela, and can you talk a little bit about your path to using synchrotrons, what brought you to where you are today, and you're a user, of course, and if you could maybe also talk a little bit about like what is it like, what do you have to do to get access to use Sirius?
Hi. So my first time in synchrotron source was in 2019 during my PhD studies. So in that opportunity, we used the third generation synchrotron source in Campinas, São Paulo, because Sirius was under construction in that time. So that was my first opportunity to work in a beamline. So in that occasion, we used X-ray absorption spectroscopy to study enzymes. I think synchrotron sources are very powerful to study enzymes, to study the mechanisms of especially metalloenzymes. So we used this technique, this facility several times to investigate mechanisms. And during my postdoc at University of São Paulo, I had other opportunity to use that time Sirius, and we could perform that work I presented before. So it was a very nice experience to compare the third and the fourth generation synchrotron sources. We can see how can we explore more our system using the fourth generation synchrotron source, and it was a very, very nice experience. So also I worked with some biomimetic electrocatalysts, and also we can explore more about the structure and the conformation and the electronic structure of these bio-inspired electrocatalysts using synchrotron beamline.
Great, thanks. And just to maybe go back a little bit more to how you get access to your facility. I think generally the model, you write a proposal, it's reviewed by other scientists, and then this is free for you, right? If your proposal is accepted.
Yeah, it's free at Sirius. We we write a proposal and submit. There are some referees that can evaluate this proposal, and we can have some access several hours in the beamline. So I think it's the same process in other synchrotron sources around the world.
Yeah. One of the things that I give tours a lot at the Advanced Light Source, and what I love to highlight is, these machines that we all work at, these are, way upwards of billion-dollar type machines. So it's not something an individual university or company can kind of build and maintain on their own. So it's so important that we have these centralized resources where everyone can come together, and that creates that international community. Now, Graziella, you were transitioning us very nicely into the next topic I wanted to go to, which is kind of the advantages of fourth generation light sources. And we've been kind of throwing these terms around, third generation, fourth generation, and just to be sure, everyone in our audience knows what we're talking about here. These generations kind of refer to the advancements in accelerator technology that produce the light. Now, going from third to fourth generation light, it means that we can have more brightness, so more photons hitting that sample, and also more coherence, so more ordering to the wavefronts of the light. Now, Graziella, you were kind of depicting really nicely what you saw as the distinction of going from the third to the fourth generation light source in your research. Maybe we can hear a little bit more from others about what it is about the fourth generation light source that is really exciting to work at. So maybe next we could go to Monica.
Yeah, so regarding from my field, which is structural biology, what fourth generation offered was several things. First one is that with the fourth generation, we got much brilliant beam, as we like to call it, because it's measured in brilliance, which mostly means it's more powerful. So there is more flux. And with more flux, we can shine our crystals with more power and get better structure out. And also we have a possibility that we can focus the beam to even smaller sizes compared to before, which also offers us that we can look at the systems that were much difficult before. Most prominently, something that that has been lacking was membrane proteins, so the proteins that are in membranes of our cells, because first of all, they're very difficult to crystallize, and when you eventually do succeed doing that, they crystallize as very, very tiny crystals. Sometimes they're like 5 microns in size, so this is very small. And collecting that with the previous size of beams, which would be the smallest one that you could do would maybe be 50 or 20, you would be shining way more than what you actually have, and then you wouldn't be able to get good data and good information out of that. And secondly, because the beam is more powerful, because we can control it better, that opened the doors that we can do stuff that was done previously at XFELS, which was serial crystallography. So serial crystallography started at FEL sources, and then it got transferred to synchrotrons because they became more powerful, which then enabled us also more to see different stuff that we weren't able to see before. Some membrane proteins, also to do fragment screening for certain drugs. One of them was also used in development for the COVID vaccine. So that opened up a lot of stuff that was not able, that we weren't able to do before, and we haven't even explored all the possibilities yet what can be possible in structural biology.
Oh, that's really exciting. Marta, tell us a little bit about what it means for you to work at this fourth generation light source.
Yeah, it's opening really doors to faster measurement, to smaller objects. We can see now things that before were hidden in the background, but we just needed to have a higher flux to see them. So we are working a lot on batteries and electrolyzers, and we can see now, for example, the electrolyte or lithium metal, which was considered to be impossible to be seen with X-rays. And now we have such a bright beam that we can see, things that before were thought to be invisible. For batteries, for example, we can now study in operando the fast cycling. This is the scope of, for example, having a car that is charged in 15 minutes. So we need to cycle it faster. So we need to investigate what happens very fast. We need to have a sub-second time resolution. We need to know what's happening on different parts of the battery. We need to have a good spatial resolution. We need to see inside real batteries. So all of that is only available now. A few years ago, it was just not possible to do it. It took like a few hours to get some, for example, scatterings, to get some tomography. So the fast cycling were absolutely a no-go. And now we can do it with like we can do it without any problem at the moment. So it's just opening the door to the next step of investigation for energy devices, basically.
Yeah, you've actually touched on an example that I have been using frequently on my tours of ALS about what we're excited about is being able to study battery chemistry on scales that matter to industry. So for you, like what would be the revolutionary breakthrough that comes in your field from fourth generation light sources?
I mean, going to really the industrial application with real cycling, that's the goal. So far, we had to simplify the batteries because we just couldn't look at them otherwise. But now we can look at real batteries with real cycling protocols, and we can see what happens in reality, and we don't have to modelize, basically. We can even see the real battery working. It's simply... That's what we need to know to advance on the battery field, for example. Same for the electrolyzer, same for many other devices where we always were missing a piece of information because we were either not fast enough or we didn't have enough resolution, or now we can see all of that.
Great. Now, Georgi, of course, in contrast to our other three panelists who work at ring-based light sources, you are working at a free electron laser. So can you tell us a little bit about, again, fourth generation light sources, and particularly what that means for FELs, and maybe as part of that as well, can you maybe highlight a little bit about the instrumentation that actually enables both that fourth generation light source as well as the research that you're doing?
Yes, of course. So what makes the free electron laser different than a synchrotron is that when we accelerate electrons, they really only have one opportunity to produce X-rays. Unlike in a synchrotron, where they constantly loop around at very high frequencies, at the free electron laser, you only have one chance. And it sounds like a very expensive way to do work, and it is, but it actually does allow us to keep some important properties of the electrons that are accelerated. And this allows them to generate very, very strong X-ray pulses. It's actually a phenomenon that you can only observe at a free electron laser at a facility like ours. And of course, there are many more springing around the world right now. So it basically allows us to do a very powerful X-ray burst in a very short amount of time. So these two characteristics turn out to be very unique. They allow us to do important kind of scientific applications that, of course, some people predicted a long time ago that they could be possible, but it took a while to actually come to fruition. Monica mentioned one of them, the serial crystallography. We actually have so much photons in a single pulse that we actually completely blow away a molecule or a virus or whatever we want to study. But because the pulses are so short in time, before actually the molecule has even chance to blow away, we can actually capture the image that all the atoms and the ions create in a two-dimensional detector, and we can recreate the structure of this molecule basically on a shot-by-shot basis. So this is a very unique capability that kind of very succinctly highlights this, large number of photons in a single pulse, but delivered in a very short amount of time. This combination is very unique. The instrumentation that, of course, we have to develop is very unique, especially on the accelerator side. So we have to learn how to generate these electron bunches and accelerate them and propagate them over large distances. Then they need to be turned into X-rays. They pass through these undulators that are, for us, it's basically a hole that's on the order of 100 meters, like a whole football field long. And you have to control the delivery of this beam to within microns. And somehow The people who work there, they're truly amazing. They know how to do that. They have a very kind of specific diagnostics. They have feedback mechanisms and all that. And it's really amazing that the beam does show up exactly where you expect it to be every day, every hour, every second. Another aspect of the fourth generation facility that is particularly interesting to me as a spectroscopist is the fact that we can really study processes that occur in nature, but we can actually understand how they evolve in real time. So, for example, we don't quite understand how photosynthesis works. It's basically the reason why we live, why we can absorb sunlight, and we can somehow turn carbon dioxide into oxygen eventually. But we don't have a good understanding of what are the individual processes that take us to these steps. And some of them occur on a very, very short time scale. And this combination of having X-rays that give you the specificity that we can interrogate individual atoms or atoms in the individual chemical environments and do that on a very short time scale is kind of a very unique combination that many of our users are taking advantage of it. But they're also having tremendous kind of breadth of new ideas of how to use the facilities. Sometimes we're actually lagging behind their ideas. So we kind of constantly have to work on our new instrumentation and kind of develop new ways to deliver more exciting capabilities.
Yeah, it's really amazing what this instrumentation advances technology are allowing us to do with the science. So Georgi, for you personally in your research or for your users, what is kind of that most exciting potential science that's going to come out of fourth generation light sources?
Yeah, so as I mentioned in my slide, we are currently basically in the final steps of upgrading our facility from a facility that works at 120 hertz. So that's how frequently the pulses arrive, to almost a megahertz. So we're about to witness a 4 order of magnitude increase in the average number of photons that we receive every second or every hour. So this is a truly an amazing leap in kind of the average brightness that large facilities have kind of rarely seen that. Maybe the last time it happened was maybe more than 20 or 30 years ago. And this will allow us to kind of expand the portfolio of work we can do in several directions. First of all, we can do far more precise experiments. So far, we're basically like a heavy hammer that we're looking for a nail to hit. Right now, we can actually interrogate systems on a much more precise way, try to interrogate them with a better energy and time resolution, try to photo excite them at a much different wavelengths, at different fluencies, and basically try to understand the behavior in much finer detail. But I want to say something that's maybe a little less conventional. What we have learned so far out of almost 15 years of operation of FEL is that there is no one particular experiment that everybody wants to do, and we have to kind of increase our performance to meet that demand. It's actually with more capabilities, our users, which are so knowledgeable, they actually come up with new and exciting and mostly unpredictable ideas how to make the best use of that. So in a way, we're kind of a little bit different from our colleagues, for example, in the high energy physics community, where they know that, oh gosh, we need to learn if the Higgs boson exists, right? So they build a large collider and they operate it for many years. We don't have this kind of overarching single goal that everybody operates their facility. We actually try to serve a broad community, invite people from everywhere, and get everybody's ideas eventually realized. So that's our excitement for the future.
That's great. That's very inspiring. We're going to turn soon to some Q&A from the audience. So be thinking if you have questions, go ahead and put those in the Q&A feature that you can find at the bottom of your screen. I did want to actually delve in a little bit more to a topic that I feel like a couple of people have touched on here, which is kind of there's multiple interactions between people at these facilities. One I would say is, as you were just highlighting, Georgi, the how users are driving the science, and this interaction between, say, a Beamline staff member who is trying to collaborate with the user to do that science and enable their science. And then there's also, of course, pushing more the instrumentation advances, whether it's instrumentation of the beamline or the accelerator itself, that allows that, that science to happen as well. So I'm curious to hear just a little bit from a couple of our other panelists who might have an interesting, I don't know, anecdote or something about something they've had to do to that beamline to enable the science, or how you've interacted with someone who works at the facility if you're more on the user side. You know, Marta, Monica, Graciela, maybe you want to jump in and give an example? Okay, Monica.
Yeah, I have one funny one. So as Georgi said, like you think about as much as you can on certain things, and you also need to follow certain regulations regarding safety and so on. So one of the things is that since we are working on a radiation source, we need to have radiation safety, which in Sweden, it includes when you're searching the inside of the hutch, it makes a very annoying sound, and you have 2 rotation lights, one being yellow, one being red. And at first, you don't see any problem in that until when you have users who have light-sensitive samples. And then you have to come up with fun ideas how to cover those particular lights, but not affect other things. And then it also is a problem because the whole thing where you put a sample is built that you have light there so you can see your sample. But if you have white light, the sample that is light sensitive will also have problem with that. So then we need to come up with different ideas, both how to visually see the sample so that we don't literally work in the dark, and also to secure our hutch that searchlights don't damage the user sample. So that was the funny one that we didn't think about until we one time that the first user with light sensitive samples came.
It's amazing how what innovation can be created with these situations. Graciela, I'm curious to hear from you if what your interaction has been like with the staff working at Sirius or other light sources.
Yeah, we interacted. We had a huge interaction with the staff from Cardinal Bobbing Line, so we could use this electrochemical cell that they developed for our experiments. So yes, this interaction is really nice because they have a huge experience, and when we are users, we only see our side. For example, I'm interested in bioelectrocatalysis, but they know everything about X-ray spectroscopy and how to do these measurements, and we can combine these expertises to get our results. So I think this interaction with the beamline staff is really important to design the experiments and get really nice results, really nice data.
Right. Well, I want to get maybe to our last prepared questions. We have time for the Q&A. Let's consider this a little bit of a lightning round. Can you each share an important piece of advice that you have received and how it has impacted your research or maybe even your life in general? Let's go first to Marta.
But maybe the best advice that I received was to learn how to get rest, because sometimes you are so excited about the experiment, about what is happening at the beamline, you just don't want to leave because there are always things happening there. You just want to stay there the whole day, the whole night, the whole week. And at some point, you need to learn how to step back and say, okay, you know what? This week, maybe I'm not going to the beamline. I'm staying in the office. I'm working on my data. I'm working on other stuff. I'm taking some days off. Because otherwise, it's really hard to... everything is so exciting. I mean, there's always something happening. It's just hard to say, okay, I'm leaving. So that's maybe the best thing that I was told, and I'm learning how to do.
Work-life balance, definitely very important, especially when you work at these 24-hour-a-day facilities.
Yeah.
Let's see, Monica, how about you?
Well, for me, the advice came from two separate people in a different time, but they're kind of the similar. One was when I attended a lecture from a Nobel Prize winner, Venki Ramakrishnan, and then later from the pioneer for Clarke, crystallography, Elspeth, when both of them said that your degree doesn't define what you're going to end up working on. Because both of them started in a completely different field compared to what they ended up working on.
As a originally trained materials scientist, now working in communications, I can attest to that. Graziella, how about you?
The important lesson I received from my supervisors at different times in different places was there is no bad results in science. Everything depends on the point of view. And there is no useless result. There is poorly explored or misunderstood result. And with this, I could learn the data analysis and the process are as important as getting the data. So do not get the expected result does not mean that the result is useless. Every result means something and should be discussed. I think this is the most important lesson that I received in the last years.
We are so prone, as well as a scientific community, to only publish the positive results, the results that look really good, but that's kind of negative results are also important to let people know when the experiment didn't go right. Okay, very, very quickly, last bit of lightning round. Georgi, what about from you? Piece of advice.
I first of all echo everything that the other panelists said, but I also want to mention that especially for the younger scientists, don't feel afraid to venture out of your comfort zone. And what I mean by that is there's so much more science that you learn how to do in your undergraduate or graduate studies. When I was in graduate school, I thought that everything was about lasers until I went to a March meeting, which is like the biggest conference in condensed matter physics, and I understand that almost nobody else is doing that. If you like what you're doing now, great. If you don't like it, there's so much more out there. Don't be afraid to look for more exciting opportunities.
That's great advice. So we have now had a couple questions coming into the Q&A, and I want to touch on maybe there's a couple of them I can combine together here. Can you talk a little bit about what is the hardest part of working at a synchrotron, and also for some of us that might be around this work-life balance aspect, and particularly how it pertains to trying to have a family, or let's say a life generally outside of the synchrotron. So maybe we can go around and you comment on whether the hardest part is something related to that, or maybe something else. Let's say, Marta, I'll start with you.
The hardest part maybe is a bit the long days, the long weeks. Sometimes we have, for example, time for measuring for our samples for, say, in-house experiments, only during the weekend or during the nights. So we try to squeeze in the experiments when you can. We don't want to lose photons. We want to use every photon. So it means that sometimes you arrive at work at 8 and you leave very late at night. So this is maybe the hardest thing to get used to. Then that's part of the learning how to step back at some point and say, okay, you know what? I cannot measure 24 hours, so I will just finish early and we will lose some photons or someone else will use them. And concerning the part of forming a family, there are plenty of people here who have kids, young kids, so I think it's totally feasible. It just needs a bit of organization and learning how to delegate and learning how to say no to taking every photons, just saying, okay, what? Like, I cannot do everything.
A thought from one of our other panelists on this topic?
I mean, I need to agree with Marta that the most difficult part is the long hours, is that when we have new experimental ways of collecting. That can be the beam time lasts the entire week, and that means 24/7. And you technically like draw from the cup who is going to do the shift from midnight to 7 in the morning. And also for in-house research, yeah, like users are the most important. So the priority for beam times is first given to users. Anything that is left over is given to us for in-house research, which most of the time is what we call like a graveyard shift, that is like after midnight, and the weekends. So sometimes that is something that can also then creep into your private life, that you with your partner want to do something on the weekend, but it's like, no, I have beam time, I have to collect stuff, or you have user support on that week time. One part on that is at least for me a bit easier is that I live in Sweden. So the laws here are quite good on controlling that you don't step too much out of bounds on that part. So the work-life balance isn't that difficult to maintain. It does get sometimes very hard, and sometimes you have to make compromises on your private life. But in most cases, it is very manageable.
Okay. Thank you so much for those perspectives. We are at the top of the hour now, so we're going to close things out. I want to sincerely thank all of our panelists for participating. This was a really engaging discussion, and maybe I will turn it over to Isabelle for some concluding remarks.
Yes, thank you very much. So thank you all speakers for your contributions. A very big thank you to Silvana and Ashley, obviously, for taking us through this webinar. I just wanted to say thank you also for all your questions and comments. We couldn't answer all of them, but I think I did try to respond to some of them to just reassure that we haven't forgotten the technology that actually drives these beautiful facilities. The technology is very important, and we will focus on some of those careers that are behind the scenes, sometimes a little bit too behind, if I'm honest. But we'll try to bring them out at a next webinar. So thank you to Sylvain, thank you to Stefania as well, and Cindy for their help and support in the background. Always important to have people that are there for technical support and helping us. So thank you all for attending. And if you've got any questions, Silvana is the person to contact after this webinar. And do visit the lightsources.org website for career opportunities. As you heard, if you're in a different field, you can always come back to a different area of the synchrotron. So don't be afraid to switch. All right. Thank you very much. And I wish you a good evening. For the UK.